Hello everyone. There is a quick check. I want to check if you can hear us and see us. So please post so that we can start our session. Can you hear us? Oh, great, great, great. Thank you so much, Prema. And I would like to start now the session. Good evening, everyone. This is Shravani. Warm welcome to all of you in Crypto Innovation webinar interview series. Today is part 6 and topic is very interesting. Secure communication through quantum cryptography. Cryptographers are first line of defense in ongoing war ranging from centuries, a war between code makers and code breakers. This is war on information. The modern battlefield of information is digital and it is wages across your phone, your computer, your laptop, and your internet. Until recently, we thought we won this war for good. We thought modern encryption is strong enough that no one can break it and we are safe. But we are wrong because of the quantum computers are coming and they are going to change the game completely. Modern encryption sends encrypted data to anyone in the world with a blink of eye, especially when public key encryption has been born. We don't have to share our secret key and can encrypt the message in milliseconds. This brilliant idea is rely on a hard mathematical problem, integer factorization. The very, very large number, which is multiplication of two large prime numbers, even the fastest computer can't factor it. This is the problem that our smartphone, laptops are using it right now to keep our data secure. This is the basis of modern encryption, and by combining all the computing power of the planet, it can't solve the problem. That is the reason cryptographers thought we are stay ahead of the code breakers. As we thought the war is won, the bunch of 20th century physicists come up with this with saying the fundamental laws of universe are completely different. Like nothing can spin clockwise and anti-clockwise simultaneously, or one object can't be two places at the time. But this is all incorrect, and it shattered everything. This is quantum mechanics, and it is a science like a science fiction. This quantum mechanics, nature of the universe, is revealed recently, and it gave birth to the quantum computers. The thing is very powerful, faster than supercomputer. This quantum computer solves biggest universal problems like global hunger, tackle climate change, and many more. But they have come with a great risk. The integer factorization, which is the basis of modern encryption, can be broken in the fraction of the second. Isn't it scary? Our so-called strong encryption can be broken in seconds, and we will be no longer safe from the hackers. Answer to this is the strong quantum safe encryption. Let's find out more about the quantum cryptography and how it is safe in the modern digital world from our guest, Dr. Anindita Banerjee. Hello, Doctor. Dr. Anindita Banerjee received her PhD from JP Institute of Information Technology, Noida. During her PhD, she has collaborated with eminent scientists in the field of quantum information, quantum secure communication, quantum computing. She was assistant professor in Women College of Engineering, Durgapur. Later, she joined as a research associate in Bose Institute, Kolkata. She had worked in quantum optics lab in Bose Institute, particularly single photon experiment. She was awarded CSIR Pole Officer at Bose Institute. She published more than 20 journal papers. She has co-authored a book on optical quantum computation and quantum communication published in SPIE Spotlight series. At present, she is working as the quantum security scientist at QuNu Labs Private Limited, which focused on quantum safe solutions for cryptographic primitive. Her research interests include quantum cryptography, quantum hacking, quantum optics, quantum imaging, quantum computing, reversible computation. Wow. Dr. Anindita, welcome to our Crypto Innovation series.
Thank you, Shravani, for the introduction. Good evening, everyone.
So I would like to start our conversation with, what are the problems you think in the cybersecurity?
Sure. So before I come to this point, you have given a very good introduction. So to that, I would like to read the lines which I want to start my, this presentation with. So it says that few persons can be made to believe that it is not quite an easy thing to invent a method of secret writing which shall baffle investigation. Yet it may be roundly asserted that human ingenuity cannot concoct a cipher which human ingenuity cannot resolve. So this is this beautifully depicts the war you were talking about, code makers and code breakers. So today we are on the verge of a new technology. So I would like to begin with first explaining what is the cryptography, what is the problem we are addressing to, and why that is such a big problem. So, so first, if we look at we know that cryptography is an art of concealing messages, and this slide tells you that this is the basic architecture of a cryptography, where Alice wants to send a message to Bob. To send that, she needs an encryption algorithm, and she needs a prior shared key, a secret key for Alice and Bob to communicate any message in secret. So if there is an encryption algorithm, there is a secret key, then the plain text is converted to a cryptogram, and then it is sent to Bob. Bob should have the same secret key, which should be secret till that time, and then he uses that with the decryption algorithm, which is inverse of an encryption algorithm, and he gets the message back. So now if there is somebody is there who has stolen the secret key or copied the key, and he looks at the cryptogram, then he can easily decode it. So not only the secure communication, but also the key distribution. The way the key is distributed to both the parties has to be kept very secret. So now just give an example, because I understand that most of the people may not be aware of what I would be talking about. So let me take a very simple Caesar cipher, a medieval cryptographic scheme. Let's say Alice and Bob both have a table which they have shared earlier. Now, if she wants to send a message, say hi, she uses the Caesar encryption, and the message HI converts into a cryptogram MN, but it converts into a cryptogram with the help of a secret key which was earlier sent. So now if you can see, if somebody gets the key 5, they can easily decrypt the cryptogram. So, and if it is a secret, then Bob obtains it, and he is able to get the message hi. Okay, so now now this was the example of symmetric key algorithm or symmetric key cryptography, where Alice and Bob both had same keys, and there is only one candidate for encryption algorithm, which is called one-time pad, which is believed to be very secure against an adversary which has unlimited resource of space and time, and still it is and this is mathematically proven. So this type of an encryption algorithm needs again a prior shared key which is as long as the message, and key which is random, and key which cannot be used twice. So this kind of an encryption algorithm was also used during World War II. The keys should never be used twice. So there was a problem of such sendings across such long keys. So now we are in the age of internet, and we realized that people had to start sending messages to each other and to organizations whom they don't know. Now this gave rise to public key cryptography. Now this is a pragmatic approach and cornerstone for communication security. In this type of an algorithm, Alice and Bob have different keys. Now, if Alice wants to send a message to Bob, she uses Bob's public key and encrypts her message, and then Bob will decrypt it using his private key. So the entire security framework of public key cryptography is based on, now this is where I'm coming to, the entire framework of public key cryptography is based on mathematical hard problems or intractable problems. Now this type of security is called computational security. So now, coming to your question, which says, what are the challenges of present cryptography? So we know that the increased power of computation, whether you justify it with Moore's law, we can see the developments. So one such example is the recently in February 2020, RSA 250, which is actually 829 bits, was
Oh,
factored. So now if this is the case, so that gives all of us an indication that anything less than 1024 bits in RSA is in danger. So now
right.
if you want to look at the quantum computing.
So RSA actually ruled the entire world for more than 35 years, and it's based on the very simple what we call it simple, but actually a mathematical hard problem that is called as the factorization. So yeah, it's really a
Yes.
threat to the industry.
So now, as you have mentioned, and as we saw in the earlier slide, the entire framework is based on classical security of intractable problems.
Right.
Now, this classical security was considered using a classical adversary, but not a quantum adversary. So now
Mm-hmm.
there are quantum algorithms which can solve these intractable problems efficiently. By saying efficiently means in polynomial time. So from super
Right.
polynomial time, it can be solved in polynomial time. So now
Right.
this rapid development of quantum computers has also posed a threat to the existence of public key cryptography. So that is one thing. And also the Achilles heel today is the fiber, the physical link, fiber tapping. So
Yeah.
several occurrences of eavesdropping at optical layer have been recorded, targeting government, financial, energy, pharmaceutical centers. So this kind of a tapping does not require a very sophisticated equipments, and there are different
Mm-hmm.
methods of actually taking out the optical signal and how much of it is needed. So all that effort is already there, and as you can see, some of the reports which I have published, uh, uh, that it is already taking place. So it is already there.
Okay.
So these are, and then of course the backdoors. So one is since it's a mathematical algorithm, so it is always easy to introduce some backdoors. Introducing
Right.
backdoors also weaken the entire security framework and gives rise to other vested problems. So these
Right.
are the challenges I think which is the present cryptography is facing, or present day it is a threat to to the security framework.
Okay, great, 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 doctor. So I would like to request audience, if you have any questions, please post it so I can, uh, talk about your questions with Dr. Anindita. So coming back to our point, Dr. Anindita, our topic, uh, where is the threat from Q?
So if we say, see, we had already discussed that there are algorithms which can solve problems, particularly integer
Mm-hmm,
factorization and logarithmics efficiently. Now, this is a reason
mm-hmm,
because the Shor's algorithm kinds of solve the period finding. So, in fact,
right.
other algorithms also, like the elliptic curve cryptography, Diffie-Hellman, they are also under the same radar. And now any security
Hmm.
protocol that derives the security based on these algorithms is also at threat. Any product or security system that relies on these algorithms are also at threat.
Right.
So now, having addressed that, if we try to look at where all, where all is it spread? So then you can start with the public key infrastructure.
Mm-hmm,
It takes the form of certification authority. And as we
mm-hmm,
have mentioned here, that mostly RSA 2048 bits are used for all the certificates. Then
correct.
secure software distribution. They use digital signatures, which use Diffie-Hellman. And examples are the software updates. Then we
Mm-hmm,
have key exchange over public channel. Now it is a
mm-hmm,
common method to establish secure communication between two people using public keys to exchange messages in public. So that is one thing, which is a big thing. We keep it aside. Then we go for secure emails. Then
mm-hmm,
VPN uses RSA and ECC are used for setting up
mm-hmm,
secure tunnel. Then
mm-hmm,
secure web browsing. So
mm-hmm.
here so here the basic idea is anything we are doing which is based on these algorithms has to be retooled to make it quantum safe.
Okay. Okay, okay. So, can you talk about quantum key distribution about like.
Yeah, so here, Shabani, I want to quickly mention this point, that because often
Okay.
people say that, how long have to we wait for a quantum computer, or when is the right time to start the process of this quantum transition. So there is a small mathematics behind it. So if you say, consider the shelf life of the data. For example, for census data, it is around 80 years in most of the countries. And then there is
Okay.
a transition time from classical cryptography to quantum safe. Now, if this is an auto update, it doesn't take any time. But if we are talking about a transition from public key infrastructure to a quantum safe infrastructure, then it is going to take more than 15 years.
Mm-hmm.
And if there is a quantum computer, because there are dedicated efforts going on building a large-scale quantum computer, keeping in mind to break these kind of an algorithms, factorization algorithms or RSA. So if that arrives before the summation of transition time and shelf life, then we are in danger. Now,
Okay.
there is we know that there is a fast progress in quantum hardware for fault-tolerant designs of quantum computing, and the
Mm-hmm.
scientists at Yale, they have laid out 7 stages for the development of a crypto-cracking quantum machine or a large-scale quantum computer. And
Okay.
as being reported, we are in stage 3. In
Mm-hmm.
stage 3, that means, and the rest of the stages will be, it's only focused on more of engineering, engineering issues. So the progress will be fast. So there is one eminent scientist, Michel Mosca, who leads the transition from to quantum safe. Now he has mentioned in global platforms, as well as this report is there in the standardization bodies like HC and NIST, that it takes about 1/7 of a chance of breaking of an RSA by 2048 by 2026, and 50% of the chance of breaking it in 2031. So we
Mm.
all need to be proactive. I mean, it is around the corner. So today is the
Right.
right time. Yeah,
Right. So, doctor, we have one question. Can we take one question in between?
yeah, sure.
So, yeah, all modern email servers use so-called transport layer security, remote data room cloud to exchange data. How do we use quantum safe cryptography for file sharing, and what are the prerequisites? This is by Chetan. Am I correct with this question, Mr. Chetan? Yeah, I mean, this is what the question is.
Okay. So we actually have there are um ways to make this communication quantum secure, and this has been prescribed by these standardization bodies in their white papers or in their working groups. And there is a way of how to make these network layer security or encrypting file in cloud quantum secure. So we have also worked on that, and we have done a secure communication, a quantum secure VPN. We have transferred
Great.
a text file using the keys in the VPN and made it quantum secure. So those things are prescribed; they are already there, and it'll be good that if after the presentation we can just get
Sure,
in touch
sure,
and I'll
sure,
explain
doctor.
that.
Sure, doctor. So there is one more question I'll quickly read. Even if we move from classical cryptography to quantum safe cryptography, any historic encrypted data that has been saved can be broken in the future. I mean, Srini.
Oh yes. So there is something called harvest now and decrypt later. So if there is something which is if there is some encrypted data in say 2020, and later and it is copied and kept, and later when we have a quantum computer, then using that these encrypted files can be broken. So this is one of the major threat
Mhm.
for present day cryptography, and that is one of the reasons that we have to start moving now. We can
Right.
do that. We can actually put a layer of quantum with the existing classical cryptography. We don't believe in changing everything. what we say is we give another layer of a quantum envelope to it, so that if there is any threat in the classical, then the quantum envelope is there to protect it.
Okay, great. So we will move on with the conversation now. So we were talking about need to be proactive, right? So can you explain about the quantum key distribution?
Yeah, sure. So here, when we talk about quantum key distribution, so we would like to address that what we are looking at, what is the quality of thing which we are going to get from quantum key distribution. So, so when we talk about keys, what would be the ideal scenario? The ideal scenario is when the adversary knows everything about the crypto system, but it doesn't have the key. So this is a proof, and this is it's known as Kirchhoff's principle. So that your security is good as the key. Then the key has to be random. The key should not be copied. In today's scenario, if there is no way to guarantee that the key is communicated, is not copied somewhere, or there is not some malicious activity which is not copying your keys, then key tampering should be detectable. So this is one of the desirable things, that if somebody is tampering with the key, then it should be detectable. So quantum will help us achieve these targets.
Okay.
So addressing your question of what is quantum cryptography, so it basically consists of two parties or two nodes, I can say. One node is sender node, which is Alice, and the other node is Bob node, which is the receiver. I'm talking about one-way cryptography. So Alice and Bob, to perform the quantum key distribution, they need two channels. One is a quantum channel, which can be a free space, which is a optical link. But this is the transmission line where we'll be sending quantum states. So the quantum phase appears here. Then we have a classical channel, which can be an Ethernet or a fiber link. And there is a post-processing which happens in the quantum key distribution, and that happens in the authenticated classical channel. And the entire security of quantum key distribution is guaranteed by the laws of quantum mechanics, or relies on the fundamental laws of nature, because quantum mechanics is gives the best description for the nature. And these are invulnerable to increasing computational power, new attack algorithms, or even a quantum computer or algorithms in a quantum computer. So this is one of the good approach of a quantum safe cryptography, and it is secure against most arbitrary powerful eavesdroppers. So this is how it is more powerful than a classical cryptography, because we consider that the Eve has got all the competence, has got all the powers of nature, and it is based on the laws of physics.
Okay.
So if we can talk about the laws of physics, which are the pillars of quantum cryptography, then one of such pillars is the Heisenberg's uncertainty principle.
Okay.
So if we talk about Heisenberg's uncertainty principle, if you look at these two values, these are the variances with which measure the uncertainty of observables A and B. For incompatible observables, for example, wave particle, they don't commute. They don't commute here. So, and reducing the uncertainty of one of A forces the uncertainty of B to increase, and vice versa. Therefore, the observables A and B cannot be simultaneously measured with arbitrary precision. So this is the basis of cryptography. So now I try to explain a simple experiment to understand, how this uncertainty principle helps us in cryptography. So I've taken this double slit experiment. In Young's double slit experiment is an example suggesting how the Heisenberg's uncertainty principle can be used for detecting eavesdropping. So consider an electron gun randomly emitting electrons over a large angular spread, and there is a metal wall with two slits, and then there is a beyond the wall there is a backstop that absorbs the electrons. So now P is the probability distribution when only slit 1 is open. P2 is the probability distribution when slit S2 is open. These two are classical in nature. Now when I remove or open both the slits, we see a quantum mechanical interference pattern which shows a wave nature. So this is a quantum
Okay.
signature. So as long as nobody is looking at my photons or my electrons here I'm talking about, I'm observing a quantum signature. So whatever I have emitted, now I can use them as a key.
Okay.
Now, what happens if somebody is trying to look at it? So QKD employs the uncertainty principle to ensure transmission data can be interfered by outside without disturbing the state. So now if there is an Eve who's trying to look into the slits that where the electron has come from, this collapses to a classical signature or a bell-shaped signature. So Bob understands that there is somebody eavesdropping and the entire process is aborted. So the keys are not generated. So we abort the process because we can see the signatures of Eve in the output.
Okay. 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 Yeah. Oh.
So if you see the result is very simple. It means that measurement will perturb the state, and if there is no perturbation, implies no measurement has been done on the system and there is no eavesdropping. So it is based on very simple rules. So this was one of the principles. Now here we would like to do another experiment. So here, if I have prepared, we have considered two bases, a rectilinear basis and a diagonal basis. They are mutually unbiased bases. So for example, in this basis, so this is, I'll be preparing a photon in, say after passing it through a polarizer with 90-degree pass axis. So it becomes a vertically polarized photon. And there is a horizontally polarized photon. So now if I know the state that it is, I have created the state, I measure it using a device which will giving me the correct answer. So when 90-degree polarized photon comes, it is transmitted, and when horizontal photon comes, it is reflected, and when 180-degree comes, it is transmitted. Now, now each photon is encoded. So now I'm trying to show that I'm encoding information on the degrees of photon, degree of polarization of photon. So I've encoded here logic 0 on the vertical polarization, and logic 1 will be my horizontal polarization. So my encoding is done. If Bob knows what I'm sending, he can measure it correctly and get logic 0 and logic 1. Similarly for diagonal bases. So here is again an equipment which will measure these bases such that if it is 45, it is reflected, and if it is 135, it is transmitted. Now I quickly come to the case. So now if Bob knows the initial state of Alice, he will be asking right question and he will be getting right answer. So asking right question or doing the correct measurement will give you right answer. Now case 2, where you do not know the state. So now you can also think of an Eve who does not know the incoming state and will try to measure the system. Or you can also think about Bob, where he will randomly change his measurement equipment and he will try to find out which is the state. Now you see that this was a 45 diagonal state. But when you asked a wrong question, the answer was in the states of the question which was asked, or one of the outputs of the measurement device. So it became vertically polarized, or it will become 180-degree polarized. So if it was a vertically polarized and you measured it using diagonal basis, so it became one of them. And it has no memory. It cannot go back to the initial state. So now you have changed the state of the system by doing the measurement. So asking wrong question or measurement will give you random answer. So now once this 45, had it been right question, you send 145-degree polarized photons, you will get 100 times logic 0. But now if you send 100 of such polarized photons and you ask a wrong question or you measure it with a wrong device, you will get 50% of the times it will be vertically polarized and 50% of the times it will be horizontally polarized. So it will induce 50% error, and you know that somebody is eavesdropping.
Okay.
Okay.
Wow, great.
I will not go more. This is the last I want to talk about.
Yeah, it's a cloning theorem. I was reading about it, so yeah, I would like to know about this quantum no cloning theorem.
So, so no cloning theorem tells you that you cannot clone an arbitrary quantum state. So, an arbitrary quantum state of a closed quantum system cannot be reliably distinguished and hence cannot be copied. So the
Okay.
linearity, so now what helps in that is the linearity of quantum mechanics. It prohibits the presence of a perfect cloning machine. So that is a principle which, because of which you cannot clone a quantum state. Now, suppose such a state existed. So now we will prove this by contradiction, by saying that let there be a cloning machine, quantum cloning machine. Then what happens? So then that it will behave like if you have a horizontally polarized photons, it will give you two horizontally polarized photons. If you have one vertically polarized photon, the output will be two vertically polarized photon. But what if it is a diagonal state, or it's an arbitrary state, right? So for cloning a general state, so if you do it how it should be, actually it should appear as if in this manner, as an equation 1. And if we are trying to do a cloning mechanism, because of linearity of quantum mechanics, this operation will be nothing but a kind of this operation. This is referring to these two equations. So now this can become this only if I consider AB equal to A and B is equal to 0. But if A and B is equal to 0, that means either A or B is equal to 0. That means either this or this state is not there. So hence, mathematically, I can say that you can actually never clone a arbitrary quantum state. So this there was a proof, and there was a lot of good arguments given to regarding that. So all that is very interesting. So finally, the no cloning theorem, then uncertainty principle, then you cannot distinguish non-orthogonal states with certainty. So these are the pillar stones. And I'm not saying that cryptography is restricted to only this principle. If you have an entangled state, there is also non-locality. So there are many things, counterfactual, QKD. So there are many principles, and there is a proper mathematics behind it, which tells you that this is a good candidate for cryptography.
Yeah, I was reading about it, and it was not accepted initially. That was mentioned, and then later it is picked up, and people started accepting, and then this whole process started. So yeah, scientists work so hard, and they come up with different principles. So going back to our entire thing, can you say that this quantum hacking is not possible? I mean, we cannot hack it.
So now that's a very broad area. Now, Shravani, if you can give me some time, so I will talk about quantum hacking. I have so that I can explain you what is quantum hacking, where do you actually hack in a quantum system, and when you talk about it as a whole product, I mean that is a different scenario, because then there are different places of attack. But when we talk about, when quantum cryptographers talk about quantum hacking, then what is the link and what are the particular areas where they look into? So that I will discuss after I think I have discussed what is the QKD.
Okay, yeah, sure. So I think we have many questions, Doctor, and so can I take some of them? You only mentioned thread to factorization based algorithm. What about the symmetric key based encryption? What is the threat to them?
So if you consider symmetric key algorithms, let me talk about AES. So AES are considered quantum safe because you see the Shor's algorithm finds the periods, and because of that period finding, the intractable problems can be solved efficiently. But if you consider symmetric algorithms, then there is something called an algorithm called Grover's algorithm, which does random data search. So now that algorithm gives you only a quadratic speedup. So you can still fight the quantum era using AES. They are believed, they are considered quantum safe, provided you can have to keep on increasing the size of the keys.
Rise of the key, correct. Yeah, so longer the size, then your AES is safe. It's something that happened with RSA also. They were increasing the size of the key, and now with the quantum era it is completely broken. I mean, we cannot say that it is RSA is safe anymore. Correct me if I'm wrong.
No, you're absolutely fine. But there can be some arguments saying that, see, the quantum computer, it is very, there is a very less chance that all of a sudden thousands or a large scale computer is built. So why not upgrading the RSA and keep increasing the key size? You know, but that is again very challenging because the
Right.
processing time in the computers for RSA will actually, if we look at the progress, then it will cross the Moore's law. So that is not possible. A study
Right.
has been
Not
conducted on
easy.
that also.
Right.
Yeah,
So same can be applicable to AES after certain time. What I feel is like as we progress into the quantum computation and how long we will increase the key size for AES. So
yeah.
that is again a question. So there is one more question. Is quantum crypto safe from fiber tapping?
Um, so if you are tapping a data which has been encrypted by quantum keys, you can keep it and store it. There is no issue. Now, if you're tapping a key, so you see the power, the optical power, and that quantum link where you're sending the quantum states or single photon states is in the level of picowatts. So if you're trying to tap it, so now what does tapping means? You're taking out some part or some fraction of the signal. You are sending only one single photon states, or you are
Mhm.
sending signal states which are so weak. So it is actually not possible. So the attacks which are there in the quantum channel on the quantum link are very different than optical tapping, because optical tapping doesn't work
Okay. So there
as
is
it
one more
looks similar.
one more question. Can we use the current fiber optical cable for QKD?
Oh yes, we use standard telecommunication optical fiber for QKD. Yes.
So one more question by Professor Sule is, once we have quantum key distribution infrastructure, do you mean to say we will not need present day public key cryptography?
Uh, that's a very interesting question, because you see, when you do quantum cryptography, it is actually not just the physics or the generation and the sending of the quantum states. There are a lot more other quantum primitives required. So and also during authentication, because my authentication duration need not be very long. So yes, we will need it, and it has to be properly strategized. And to say that once the quantum cryptography comes or quantum safe encryption algorithms comes, they will totally vanish is not at all possible. It is not like that.
Okay, so we
They
will
will
continue with our
exist.
discussion.
Yeah. So now if we look at quantum QKD algorithm, so if you can see that this is a quantum transmission box. In quantum transmission box, Alice and Bob will decide which QKD protocol to follow. For example, they have chosen BB84 protocol. So Alice system will have a quantum state generator. She will have a quantum state encoder. Then it will be sent to Bob. Alice will also have a random number generator. Then you have Bob. Bob will have a decoder, will have single photon detectors, will also have a random number generators. So this is the first step where they send the raw keys. So once the
Mhm.
raw keys are sent, then you have a process called sifting. In sifting, it is basically dependent on protocol. If you're doing basis dependent protocols, then you will factor, or you will have to drop off those cases where they don't match. So this is again very specific to the protocol. And then of course there will be other filtering required. So let me say, after the raw transmission and sifting, we get some correlated bits at both Alice and Bob's side. So that is
Mhm.
called, now the process for error correction will begin, because we see that we are dealing with non-ideal components, and there will be some other factors. So we'll have to compute the error. Now the error will be because of imperfections and because of eavesdropping, which you cannot rule out. So that has to be corrected. So for that, Alice and Bob will exchange some random numbers will say suppose a bit string u, such that the knowledge of u with the bit string of which Alice has should have little uncertainty with the bit string with Bob has. So this is basically an error correction algorithm. And a good error correction algorithm will reduce the information leakage, because this is happening in the classical communication line. So certain bit strings are exchanged. So that information leakage has to be quantified, and Shannon's entropy and conditional entropic functions are used to quantify it, and that is taken care of by generating the secure key, or correcting the errors in both the bit strings. So this is again, a lot of research is done in the analysis, because when you look at the components, they are not ideal components. And also when you design the security framework, you consider some assumptions. You always consider some assumptions. And then how much is the trade-off between the real theoretical components and the device performance? How much is the leakage? So all these are analyzed and put together by some compression factor, which is called privacy amplification. In privacy amplification, basically it's a the bound. There is a bound on average collision probability, which allows the two parties to make each mutual information exponentially small. So after all these mathematical and processes using cryptographic primitives and the quantum key exchange, finally you obtain a secure key, which will be or I should say, the secure key is finally generated. So you see, earlier during classical key distribution, you already generated a key and then you distribute it. But in quantum cryptography, the keys are generated in insecure public channel, which is a quantum channel. So the secure keys, it is an art of generating secure keys in presence of an adversary. So this is the beauty of it. I have explained this keeping things very general, and all of them can be specific to the protocols which are used. The protocols will be specific to the source you want to use. It is a single photon source or it is an entangled source, which are also dependent upon where exactly you want to do the QKD. You want to do it in free space, or you want to do it in fiber. So there are many things which you have to keep in account to develop a QKD protocol.
Okay.
So are there any questions, or I can move to the
there are a couple of questions. Okay. Heisenberg, can you please repeat the Heisenberg example, please? That's what the question. If you have time, you can do it.
yeah. So I think let's quickly move on. So I want to also finish this. So finally, what we want from this quantum cryptography is we want to use the keys. So if you want to use the keys, okay. So then the composable security framework is very important. So the main requirement of security is composability. This implies that security of key generated could be used for other cryptographic activities. For example, one-time pad needs perfect key. So what is a perfect key? It refers to uniformly distributed, but the events or the string where values are completely independent of each other. And so they have to be independent and uniform. So that's a perfect key. So here is a framework, or I mean, I can be quick. So let Ka and Kb be the identical, be the key strings of length m generated at Alice and Bob. They form an ideal key set. The joint probability is given by this, but the probability that they differ, because now they are already error corrected, so they differ is 0, and they have to be equal. Then in quantum mechanics, the ideal key state is represented by density matrix, which is shown in equation 2. It is interesting to note that in the ideal case, the each state is totally independent of the key. But in realistic implementations, Alice and Bob cannot generate an ideal key at both sides without some failure probability. So in probability theory, the total variation distance used to characterize the two probability distributions is a variation distance, is actually the trace norm. And now that is coming out in equation 4. So finally, I will. So if you want to talk about it more, then maybe we can take it up. It's a little more technical. But finally, the last equation 5, I would say that composable definition of security is a most modern definition of security, and it is based on trace norm, trace norm 1, right? And here tau key is the completely mixed states, and rho e is the state of the adversary. So this kind of a rigorous mathematical framework was developed to enable the use of QKD for present cryptographic applications. So I can, so now since we have discussed the QKD algorithm, and we have discussed also we have looked into the principles. So I will go through this very quickly. So this is a standard BBA-T4 protocol. Alice generates these 4 states, non-orthogonal states. Now, after generating, they are passed. So there's a random number generator, which I had mentioned with the Alice and as well as the Bob. So they send these states. This is a raw key transfer. When Bob receives it, so the raw key is generated at the Bob side. Then based on that, there will be some basis selection done. So they have measured in the right basis or in the correct or in the wrong basis. So that is given by. So let me just explain it from here. This slide. This is a okay. So random numbers were generated. So these are the random photons which have been generated. So Alice qubits are vertical, then diagonal, horizontal, diagonal. So qubits reaching Bob, because some of them will be lost because of the fiber attenuation. But let me say they are still there. So in that case, this fills up here and this fills up here. Now Bob's random basis. Now Bob will be using basis randomly using this random number generator. So if he uses a rectilinear basis, it is correctly detected. If he uses wrong basis, the state is 45 degree and it is a diagonal basis. So it becomes randomly 0 and oh, this is a correct basis, so it becomes 0. So this is again horizontally light, and this is a diagonal basis, so this is wrong, but randomly it becomes 1. Again, this is wrong, so it becomes 0. It can become 1 also. So like this, it propagates. So detected bits are 1, 0, 1, 0, 1, 0, 0, 1. Now Bob will tell Alice his measurement basis. Alice will tell Bob which bits to keep and which ones to discard. So after that, this is Bob's sifted key. So after the sifted key, they will calculate the information leakage. And from this 1, 2, 3, 4, 5 sifted key, it will get reduced to less than half, or maybe depends upon the errors also. So compression will happen. So you see the length of the final key and the secure key and the length with which it was sent is always the ratio of something about 1/3. So something is lost because of the fiber attenuation, something is lost because of the basis, something is lost because of the electronic synchronization. So finally we are left with something, but something which is very, very secure. So yeah, so then I can come to hacking, to your question.
Yeah. So there are actually lots of questions, doctor. So can we take some of them? So if we detect EVS dropping, I would stop the process of generating more key. This means I could potentially initiate denial of service by trying to EVS drop.
Please come again.
If we detect EVS dropping, I would stop the process of generating more keys. This means I could potentially initiate the denial of service by trying to EVS drop.
Yes, so this is a good question. So somebody can inject light and they try to stop this the working of the QKD. But in that case, let me tell you that injecting light is very dangerous. It will hamper the because we have single photon detectors. They have a bound on the optical power which they can take. They will go for saturation, and I'll be able to know that some flaws is happening. but that comes with a greater cost. So prevention are taken. Since we know that these kind of strategies are there, there are some security patches and security areas where we inject some kind of an optical device and try to take care of that. Having said, we'll be able to come to know of the eavesdropper after one round of QKD. So suppose my threshold was something at say 2%, but because of eavesdropping, as you said, we had mentioned that because of eavesdropping, because of the measurement, the errors will increase. For example, if I give you the BB84, if somebody tries to eavesdrop it by man-in-the-middle attack, it induces error to 25%. So I can see that range, and I will immediately drop the entire keys generated. Now, when I go for network QKD network, then this kind of thing where either injecting or cutting or some link is not working, these kind of things can happen, and we have to take care of that.
Okay, there is one more question. AES 256 is safe, not AES 128.
No, this is so this is with respect to a quantum computer. So
Not sure. I mean, this just
as and when the computational speed is increasing, the AES 128 has to move to AES 256. And now, when we say that from the perspective of a quantum algorithm or Grover's algorithm, which gives you a quadratic speedup, so the security level of AES 256 on a classical computer is will be equivalent to AES 128 on a quantum computer. So I can compare the security levels in a quantum computer, which uses Grover's algorithm to hack it, and a classical computer. So that way I can drive a similarity.
So what's the application quantum no cloning theorem, where it is used?
Oh, it is used in the cryptography itself. You cannot copy a quantum state. You cannot keep, suppose I'm encoding a state, a photon in its degree of freedom, say phase or polarization. So that information is stored there. If you try to measure it, you are going to disturb the state. So no cloning theorem will not allow you to copy the state.
So quantum hacking are possible is the question. So we will come to our discussion.
Okay. So quantum hacking is of course possible, and it has been. So you can see the table for yourself. Photon number splitting attack. So the attack happens. Now let me talk about the quantum channel. The attack happens on the quantum channel, and the attack happens on the equipments of the quantum devices. So now, if you look at the security proofs of generating secure key proposed by Gutesman, Lowe, Preskill, and Wittgenhaus, GLLP. So that is a recent proof, and they have considered the security of against an imperfect device, which can be a source and which can be detector, because these are realistic devices. These cannot be perfect. So those considerations are also already taken. Now, when this technology became more popular, then people from other disciplines like electronics and electrical, now they try to exploit attacks attacking the detectors, and also the security assumptions. For example, I consider the phase to be randomized. So when I'm using different kind of sources, if that criteria is not met, then there's something called phase attack, which is done. Then there is something called basis dependent detector attack. So that is what detector blinding attack is all about. So these systems are attacked. But having said, these are intercept and recent attack strategies, where each and every photon is attacked. It is still very basic clear attack. If I go to the next slide, so this is the attack, which is so this is something which is theoretically proposed, and these attacks, most of them comes under incoherent attack. So they kind of copy the state, try to copy the state, or try to detect the state, and then they resend it or try to measure the output, having a system similar to that of a Bob. But all of them can be countered first of all, there exists countermeasures for all of them, and they can be countered by making the system more intelligent and also making the detection system or Bob or the detectors more intelligent. And this is something which we are also working upon. So then there is a broader attack, because as I told you that we give the attack of the power of physics. So there's something called collective attack, and the most general form of attack is called coherent attack. And these kind of attacks, if we don't, if you're running out of time, because these kind of attacks are possible when you have a quantum memory and a quantum computer. Or for example, in coherent attack, you need a probe of huge dimension. So she attacks the entire photons with one probe. She needs a quantum memory of huge dimension, and then she measures them. So this is the most general attack, which is theoretical in nature. And collective attack has been proven to be strong enough as that of a coherent attack. So basically, the security against eavesdropping is one of the very difficult areas, and it is extremely difficult to prove a protocol secure against all the attacks, the most general coherent attacks. Yeah. So
okay.
So this is a challenge. Yeah.
So there are many questions, Doctor. I must say that, but we are running out of time, so we will just continue with your presentation.
Okay. So I'll just quickly take you through. This is the product which we have developed. So I also have a video of our product for a minute. So we can go through it at the end, I think, if we have time. This is what the Alice node looks like. Yeah, so this is what so when we do QKD, we have two nodes. One is the sender and the other is a receiver. So this is one such node. So we have two nodes, and then in between we have a quantum channel, which can be a fiber spool. So we have taken our systems to different organizations, Microsoft and Cisco during the incubation competitions, and also we have demonstrated key exchange. We have shown how the keys are generated and how they can be used in commercial encryptors to communicate. Yeah. So this is the product, and this is the video. If I can just take you through quickly. So in the Bob side, which is a receiver, you can see the clock. The two systems has to be synchronized, and these are the Ethernet ports through which we do the classical communication. And there will be some LEDs at the end, which tells you the status of the processes which are happening. For example, there will be an LED for when the quantum bit error rate goes beyond the threshold. Then this is an alert. So when the systems are getting auto-tuned, then there's an indication. So there are different indicators in the system which tells you about the different processes which are happening. And this is the optical link or the optical fiber which through which Alice and Bob communicates. So this is the quantum channel, and you have here spools of 50 kilometers. So if you want to see if you want to do transmission of 50 kilometer or 100 kilometer, we have two spools. We connect them and we do a quantum transmission of 100 kilometers. So this is Alice. This is the optical fiber link, and these are the Ethernet ports. So again, the LEDs are also here, which glow as and when it executes each and every processes. So I'm quickly taking you through this Alice and Bob system. And this is something which we have demonstrated. So so we had two systems, Alice node 1 and node 2. We had three links. So one was an optical link through which we synchronized both the systems, and then the other was a quantum channel, which was a 15-kilometer link, and then we communicated classically using a Ethernet port, Ethernet link. And then these are the commercial routers. So there was a protocol which is specific to the organization, which was given, and we had sent the keys generated from our QKD system to the routers, and then communication was established using cloud amongst these two routers. These are the screenshots of the screen showing the keys are generated, and the length of the key and the error rates are all mentioned in these snapshots. So I have discussed this work in a paper called a Practical Solution for Secure Network, in a quantum computing era, co-authored by me and Karunakaran sir. And if you want, then I can circulate that paper if anybody is interested. That how
Sure.
we have, yeah, we have also discussed up the protocol for the POC we have done. And these are the three products. One is a quantum random number generator, and the other is a RMOS, which we had shown, and the other one is a quantum secure platform. So, so this is a quantum random number generator. It generates around 1 megabits per second, and there are different solutions we are working around the product. Similarly, for QKD, not only for organizations but also for academic institutions, and there are other solutions as well around this product, and we are expanding the quantum communication from point to point to a network using the CODOS platform. So this is something I wanted to show, and if we have time, I can discuss about I can show the quantum networks which has been
Doctor. Yeah. No problem. You can take some time.
Okay.
The topic is very interesting and very new. There are a lot of questions actually. I'm really sorry I can't take them because we are running out of the time.
This is a point-to-point QKD. So the distance can be around, if it is a fiber-based system, can go till 200. Actually, it has gone till 400. So there are different ways of increasing the distance. One of them is either detectors or, and there, I mean, we can go about it more. But fiber to fiber, usually, if I take the standard parameters, it is around 150 to 200. Then there is a mechanism of how we send the key to the encryptors, and how does the encryptor understands which one to refer to, because we send them keys in different slots, and the part of the key becomes a key ID, and the key ID is transferred to the Bob through this communication channel, and then Bob picks up the random numbers associated with the key ID and decrypts the message. So here I want to show you that the key is never sent. The keys are generated in the QKD boxes, and they never travel in the classical channel. They never travel. So it's only the key ID, which is again a random set of numbers, which is a part of the key, is traveling here, and then I refer to the it refers to the keys which are needed for encryption and decryption.
Okay.
So in this mechanism, I can go from multi nodes, and yes, again in that paper we have mentioned how to use QKD setup RMOS from point to point to increasing it, say at a distance of 500 kilometer or 1000 kilometer using multi-hopping. So this is a hopping way of doing a QKD using trusted courier.
Okay.
So this was one slide I wanted to discuss because China is leading in testing the quantum networks. So one of the things which they have done is the from Beijing to Shanghai there is QKD. They have implemented quantum key distribution network, which is 2000 kilometers long and has 32 trusted nodes. This has been done in with 1550 wavelength and generating a key rate of about 20 to 30,000 bits per second. And apart from that, apart from this, and this caters to banks, and the main players are basically banks and power grids. Then they have also tested a wide area network from HiFi to Woohoo, and in this they had run a 5,000 hour test, and they provided a test bed for realizing, standardizing, and designing QKD networks. Apart from this, they have also done a metropolitan area network where they have deployed quantum network, and they serve government, military, finance, and electrical sectors. And of course, we know the MISIUS satellite. It is an intercontinental QKD between China and Europe, and linking 7,600 kilometers. It is based on entanglement distribution, and it has done video conferencing as well, right? And this is their plan where they want to extend this to more terrestrial QKD networks.
Okay.
Yeah.
So where we are.
Yeah, so these are the other, I think these are the ways we can extend the quantum network in our country. This is the ring configuration and this is the mesh configuration. And these are very specific to organizations. So if there is a requirement, then it is better to sit together and understand how to integrate it, what is the best way to integrate it and get this done. Yeah, so with this, this is the last slide. This shows the vision of our company where we want to give an envelope. So the classical security is already there, and a lot of challenges it is facing because of reasons we have discussed. And we intend to give a quantum layer of security on top of the classical layer to prevent it against future attacks and to make it quantum safe.
Okay, so I think we will take couple of questions because there are so many questions. So we will take some of them. Um, okay, we are trying to achieve protection from classical adversaries. If the quantum computers come into existence, then isn't there a huge chance that we will have quantum adversaries too? Then what will be our measures?
See, right now we are fighting against few algorithms which had been proposed, and like the Shore's algorithm and Grover's algorithm, which addresses certain problems on which the current cryptography is based upon. But as and when the quantum computer is coming, and you must have seen the survey that during this period, the quantum computer IBM had millions of users. There has been an increase. So many people are looking into it now. So when many people look, then they can come out with new ideas and they can come out with new algorithms. So it is actually a challenge to understand the whole picture. Actually, we should look into the complexity classes. What are the problems which quantum computer can solve? What are the problems which a quantum computer cannot solve? So can we base some cryptography or mathematical hard problems around it, which will be safe? Uh, Having said that, PQC is exactly what it is. These are classical algorithms which are believed to be quantum safe. So that is a challenge which I think which the world is facing. So what to say safe and what not to say safe, and which one to say safe till what period. So yeah.
So there is one more question. How good is ECC compared to RSA?
Um, from the quantum perspective, as I told you earlier, we can find out the period, and that is something which takes which reduces the problem, both the problems, to a polynomial time up problem. So from quantum perspectives, they are the same. But having said, there can be some developments which I won't be able to put forward. But then one thing for certainty which I've mentioned is these are solvable in polynomial time. Both the problems are solvable in polynomial times.
Okay. So one more question, Madam. You said the quantum will be the wrapper on the available scheme, but if the available scheme itself maturing, then using quantum will give it the security.
So now, what do you actually mean by the present scheme is actually maturing? So if I say if I say that the present scheme, you are saying that yes, I'm increasing the key size and making it quantum safe, then yes, as Shavani herself has made a comment that till how long can we keep on increasing the key size? That is one thing. So and or coming out with some new algorithms which are robust against quantum computers. But again, are they proven to be quantum safe, or we have to again take the risk?
Right, correct. So there is one more. Is a quantum pseudo-random generation possible? That is a randomness which is perfectly repeatable.
So
Professor Sohail.
when you generate random numbers, It is either by some algorithm, mathematical algorithm that is called a pseudo-random number generator, and it is either by some hardware. So quantum is a hardware. So you're generating the random numbers from a physical process, and that is not repeatable because it is intrinsic. The randomness is so intrinsic in it that even if you give the same initial condition, um, it doesn't give you the same output. It is
Okay.
based on probability, and the output is always random.
So
If I'm
government
missing
has
one,
announced a, sorry,
yeah.
government has announced a big amount of quantum computing budget. How and where is the planning to be used? Defense, space research, or in government ministry?
See, it is a very good move that our government has taken step in this direction and wants to build up a quantum computing center, and even choosing the superconducting qubits as the future for quantum computers is a very good candidate. So all that is good, but having said that, you need to make your communication system or cryptography also quantum safe. So quantum computing, increasing the capability or developing a quantum computer will give you advantage in many areas, but also you will have to, I think, put in effort in realizing the networks which I was talking about. Those kind of networks should also be deployed, or we should also be start thinking
Yeah,
in that direction.
right. So, do you need a quantum computer to perform quantum cryptography, or is it just an algorithm that can be applied using classical computers?
Okay. So quantum algorithm is realized using optics. So if you look at the box, let me just go back to the box which we're talking about. So this box, so it has a quantum algorithm running in it. Those algorithms are realized using optical elements, and the optical elements are driven by electronics, right? So this is not a theoretical algorithm running on a classical computer. These are actually small quantum computers because you have single photon states generated inside it, and which are very fragile, and it needs an it's a big engineering challenge to make such a product because dealing with single photons, and it's a very difficult task, you know. So we are actually generating these single photons, encoding them and sending them, doing a quantum transmission. So this is not a classical computer. And yeah, so please come again. So I think did I address this question, because he was talking about I believe that I thought that he's talking about a classical algorithm and a classical computer, which is absolutely not true for
So I'll
QKD.
repeat the question. Do you need a quantum computer to perform quantum cryptography, or is it just an algorithm that can be applied using classical computers?
So I don't need a quantum computer to do a quantum cryptography, because you see, in a quantum computer you are processing the qubits in a place, right? And in a quantum cryptography, it comes under quantum communication. So the photons are your qubits. You are sending them from one place to the other. So they both are very different. And classical computers are needed for post processing. They use higher speed electronics, but this system is entirely quantum. We generate the quantum states, and this is actually a small quantum system, both Alice and Bob boxes.
Okay, so I think this is last question I would like to take, because we are already late. So can the quantum key be sent via wireless channel?
Free space. Yeah, we can do free space QKD. Yeah, that is
Okay,
possible. So yeah, that is just changing the medium.
okay. Mm. So there is one interesting question. Will it eliminate the reliance on current crypto algorithms?
Um, First of all, we are not changing the current algorithms. We are saying that we want to add a layer of quantum onto it, and in future, with carefully analyzing and studying, we can start retooling the cryptographic infrastructure as and when needed.
Okay. So thank you so much, Dr. Anindita, for your time and valuable information about quantum cryptography and quantum key distribution. I must say the Indian quantum researchers are working really hard and trying to win the war with the quantum code breakers. Soon the new era of the quantum will begin, and I'm sure our researcher will be ready with the quantum safe world around us. So no need to fear. I think we can rely on our cryptographers, and with the help of our Indian researchers, we will be soon Atmanirbhar. I'm sure all the attendees must be contented with this discussion. Dear attendees, thank you for being wonderful audience, and thank you so much for your thought-provoking questions. We will come up. I would like to announce here that there will be one more session by Professor Gautam Paul, ISI Kolkata, based on classical transition from classical to quantum cryptography. So yes, next session, please do join, and it will be again on the quantum cryptography. So we will come up with more exciting innovations in the next episode. So stay tuned. Until next time, stay safe, stay secure. This is Shravani signing off. Thank you so much, Doc.
Thank you.